Well, welcome. In this video, we're going to be looking at some principles of probability. In the previous video, we were introduced to this idea of probability. What we're going to be taking it, obviously, one step further in this next video. In this video, we're going to be looking at mutually exclusive events. Now, it's important to understand what is a mutually exclusive event. Let's summarize in this last sentence here. If we have two sets, A and B, and they don't have any elements in common, they are called disjointed sets or mutually exclusive sets. And addition is going to be what we're going to use to find the number of elements in the union of those two sets. So anytime we see a symbol like this, A union B, or anytime we're using the word or, if we're trying to find the probability of something in A or in B, that's referring to the union of those two sets, in which case we're going to add those probabilities together. So we have the additional counting principle for probability here. We would take the probability of event A plus the probability of event B. For example, let's look at this situation. This is, again, a situation we saw in the previous video where we were looking at the sum of, or looking at two dice being thrown. When it says write the possible sums when two fair dice are tossed, well, we could have a sum of 2. That would be the smallest sum, because we could have a 1 and a 1. Well, that makes 2. That's the only time that's going to happen. We could have a 1 and a 2, or a 2 over 1. That would add up to be 3. So we could have a sum of 3, a sum of 4, 5, 6, 7, 8, 9, 10, all the way up to our largest sum, which would be 12. Now, part B says that each possible sum be an event. Find the probability of each event. Now, I'm not going to take the time and find the probability of getting a 2, 3. I'm not going to do all of these. We'll just do some of them. Let's say we want to find the probability of getting a 2. Probability of getting a sum of 2, I should say. And that only happens one time out of all these 36 possibilities. It would be 1 out of 36. Well, let's say if we wanted to find the probability of getting a sum of let's say 7, for example. Again, this is the probability of getting a sum of 7. We see that happens in this diagonal. So there's a total of 6 times that happens out of 36, which would reduce to 1 out of 6 times. So those are just two examples. Again, we could do this for all of these different sums. But rather than take the time to do that, we'll just look at a couple here. Well, let's look at part C. It says find the probability of each of the prime number events. Add them to find the probability that the sum of the face-up numbers is a prime number. Well, our prime sums would be a sum of 2, a sum of 3, a sum of 5, 7, 11 is also prime. So we'd have the sum of these 5 prime probabilities. So let's start with the probability of getting a sum of 2. We would add that to getting a probability of a sum of 3. Add that to the probability of getting a sum of 5. Add that to the probability of getting a sum of 7. And finally, add that to a probability of getting a sum of 11. And this would give us the probability of rolling 2 dice and having a sum that's a prime number. So the probability of getting a 2, we'll leave these in unreduced form. It'll be easier to add these all together, because remember, to add these all together, since we're going to be working with fractions, I have to have a common denominator. So probability of getting a 2 would be 1 out of 36. The probability of getting a 3, a sum of 3, well, that happens 2 times out of 36. Again, since we're going to be adding these together, we're going to leave these fractions in unreduced form. The probability of getting a 5, well, that happens 1, 2, 3, 4 times out of the 36. The probability of getting a 7 happened, like we already said that one, that was 6 out of 36. And the probability of getting 11 would be these 2 times out of 36. So if we add all these together, we can see that our denominator is still going to be 36. Add the numerators together. 1 plus 2 is 3. 3 plus 4 is 7. 7 plus 6 is 13. 13 plus 2 is 15. So we get 15 out of 36. That can't be reduced, so that would be our answer. Now, when two events are not mutually exclusive, that means they have outcomes in common that overlap. The set of overlapping events of elements in A and B are called the intersection of the sets. And we symbolize that using this symbol. So A intersection B. That's going to be handy for this next part we're going to be looking at. Well, in this first part of the diagram, they're showing what we talked about at the beginning, where we would have a situation that would be mutually exclusive. So the events in A and the events in B have nothing in common. That'd be like a situation involving maybe where we would have a coin being flipped and a spinner being spun. They don't have anything in common. But there are situations where we have events A and B where there is going to be some overlap, in which case that overlap section is referred to as A intersection B. Let's look at some examples now. It says, suppose at Edina High School, 298 students study only French, only Spanish, or both languages. Edina reports that there are 115 students that study French and 209 students study Spanish. But because 115 plus 209 is more than 298, there must be students who study both languages. Our goal is to figure out how many students study both. Let's look at a diagram here to help us out. So this would be a situation where there would be overlap, similar to that first diagram where we would have set A and set B. Set A, this will be our French students taking French. Set B, we'll have this as our students taking Spanish. We know that there are 115 students taking French. We know that there's 209 students taking Spanish. But since as a whole, we know that as a whole, so A union B, so together these two sets are going to equal 298. So there's 298 students that study only French, only Spanish, or both languages. So our goal is to figure out how many of them are in that intersection. We're going to call that intersection X. So that is going to be the students that are studying both French and Spanish. So that means that there's some students that are just studying just French. Well, that would be the 115 students that are taking French minus those that are taking both languages. There's some students over here that are just studying just Spanish. So that would be we could represent that by taking the 209 that are studying Spanish minus those that are studying both French and Spanish. So that would be minus X. So I'm going to come up with an equation now. So my equation will be written like this. 115 minus X, referring to just those students that study just French, plus the students that study French and Spanish, plus the students that only study Spanish, which would be the 209, minus X. Together, that's going to equal 298 students. So now to solve this, I can see that, well, negative X plus X is 0, and 115 plus 209, that's 324. Then I still have this minus X equals 298. If I subtract 324 from both sides, I'm left with negative X equals negative 26, meaning that X equals 26. There's 26 students that are taking both French and Spanish. That would be my answer. Let's try another one. Here we have a situation involving Jamie and Rhonda had to make up their FST test after school. Mr. Murphy told them they could come in no earlier than 3 and leave no later than 4. Jamie took 38 minutes on the test and Rhonda 51 minutes. For at least how many minutes were Jamie and Rhonda taking the test at the same time? Now that 3 o'clock to 4 o'clock gives us an hour of time, so there's 60 minutes that we're working with, so we're going to have a total of 60 minutes time. So if we look at, there's going to be some overlap where they're going to be taking the test together. So we'll have set A, we could have as being, we'll have that be Jamie's time taking the test. And then we have Rhonda as set B. And we know that Jamie took a total of 38 minutes. and Rhonda took a total of 51 minutes. And there's going to be some time where they were taking the test at the same time together. So to figure out how much time just Jamie took on her own without Rhonda being in the room, that would be 38 minus x. The time that Rhonda spent taking the test when Jamie wasn't in the room would be 51 minus x. And so again, our goal is to figure out what x is, which will represent the number of minutes that they were both took the test at the same time. So we would set this up to say 38 minus x plus the time that they took together, which would be x, plus the time for just Rhonda, which would be 51 minus x. Together, they only had 60 minutes, so that would be, our total here would be 60. Again, the 60 minutes is from the fact that they had from 3 o'clock to 4 o'clock. So now we're going to add these all together. So 38 plus 51 gives me 89. A negative x plus x, well, those cancel out, but we're left with that minus x equals 60. If I subtract 89 from both sides, I get negative 29. So what that means is that it took, or there was a period of time of 29 minutes where together they were taking the test at the same time. So that would be your answer. So again, this was a situation that was not mutually exclusive. The two events had overlap, which gives us a situation like this where we're going to have to know when we're dealing with a situation where there is overlap, how to find the probability. Now it's very similar to the previous one, but we have to take into account the fact that there's going to be overlap, so we're going to subtract that probability of the intersection of those two events. So let's look at some examples now where we're going to have to apply the situation. And what I've done is we're talking about those six-sided figures, or not six-sided figures, we're talking about the situation of rolling two dice. So I have this table to help us as we answer these questions, so we can refer back to it. So it says a pair of 6 dice is thrown. If the dice are fair, what is the probability that the dice shows doubles or a sum less than 10? So again, we're looking at a situation dealing with the probability of getting doubles, or, so this is going to be the union of the two, a sum less than 10. Now we need to ask ourselves, is this a situation that's mutually exclusive or not? Is it possible to get doubles that are less than 10? And it is. This is not a situation that is mutually exclusive. So we have to take, so the way that we're going to do this is we're going to take the probability of getting doubles plus the probability of getting a sum less than 10. But then we're going to subtract from that the probability of getting doubles and less than 10. So looking at this situation, so this is, we have a, so our doubles, there's a total of 6 times out of 36 that we would get doubles. Plus, we want to look at all the possibilities of getting a sum less than 10. So here's where we have our sum of 10 would be the 6 and the 4, the 5 and the 5. So all of these here are situations where we have a situation, or we have a sum less than 10. So that's a total of, well, let's see, we have 3, 4, 5, 6 that are not. So that means we have 30 here that are less than, have a sum less than 10. But now we're going to subtract from that the number of doubles that are less than 10. So we have a 4 and a 4, a 3 and a 3, a 2 and a 2, and a 1 and 1 that are all less than 10. So we're going to have to subtract from that the number, because basically these are being repeated. So we don't want to count these twice. So that's why we're taking them away. So we have 4 out of 36 that are being repeated. So if I add those together, obviously we're going to have a denominator of 36. So 6 plus 30 is 36, but minus 4 would give us 32. So we have a 32 out of 36. Reduce that, and we get 8 over 9. Which, if we want to write it as a percent, which is about an 89% chance. So let's look at another one together. Move this out of the way. With the same dice, what is the probability that the dice shown is a sum of 7 or 11? Now we got to ask ourselves, is this a situation that's mutually exclusive or not? Is it possible to have a sum that's 7 and that's also 11? No. So this is one where we're just going to add the two probabilities together. So we're going to first figure out what's the sum, what's the probability of getting a sum of 7. Let me actually move this out of the way again. So the probability of getting a 7 plus the probability of 11, these are exclusive. There's not going to be a sum where there's both 7 and 11. So the probability of having a sum of 7 is 6 out of 36. The probability of getting 11 happens just these two times. So 2 out of 36. Add those together, we get 8 out of 36, which reduces to 2/9. Or we could say that it's about a 22% chance. Now, why don't you guys try this one on your own? Actually, try these next two on your own. So again, I'll move this out of the way so we can see, whoops, what's going on here. I'll move it down here. So it says, what is the same, using the same dice, what is the probability that exactly one die shows up a 3, or the sum of the numbers is greater than 9? So you want to figure out, is this a situation that's mutually exclusive or not? Is there a situation that we can have a die that shows up as 3 and a sum that's greater than 9? So you need to ask yourself and figure that out on your own. And then I want you to do the same problem, or do the example 4b where it says with the same dice, what is the probability that the dice shows up doubles or a sum of 8? So is that a situation that's exclusive or not? So I want you guys to take and pause this video and work on both of these examples using the information. Maybe if I do this you can see it all. So why don't you pause the video and hit play when you're ready to check to see if you've got these two answers correct. Okay, well let's see how you did on this first one. On this first one, you should see that these are they are mutually exclusive. It is not possible to have exactly one number showing up a 3 and having a sum greater than 9. So the idea here too is that it's exactly one number that's a 3. So we're not going to count the 3 and the 3. So what things that are circled in red are all the times that we have an event where we have exactly 1 3, and there was 10 out of 36 times where we get exactly 1 3. And the probability that the sum is greater than 9, well, there's a total of 6 situations, that's what's circled in purple, where we have a sum greater than 9. So 6 out of 36. Together, that's a total of 16 over 36, which reduces to 4/9, or 44%. Now, let's check to see how you did in example 4b. So here, you should have gotten that the probability of getting double and the probability of getting a sum, which should be equal to 8, is exclusive, because there is a situation, as we look at the diagram here, there is a situation where we have doubles that's exactly equal to 8. So we have to subtract that because we don't want to include it twice. So we have a probability of getting doubles as 6 out of 36. The probability of getting a sum of 8, well, that happens 5 times out of the 36. But again, this situation here has been counted twice. We have to subtract it. So we're going to take away 1 out of 36. And when we do that, you get 10 out of 36, or 5/18, which would be the same as 28%. Now, there's one more thing that we need to talk about. Let me just delete this. And that's that sometimes events are mutually exclusive, and their union is the entire sample space. Such events are called complementary events. The complement of an event A is called not A. So, page 370, if you want to look in your book, there's some examples of events and their complements. But let's look at an example here. Well, first off, this theorem for the probability of complements is that if A is an event, then the probability of not A, all we have to do is take 1 minus the probability of probability of event A happening. So to illustrate this, let's refer back to the example that we looked at with the 298 Edina students studying languages in example 2a. Now, if a student is selected at random, what is the probability that he is not studying both languages at the same time? Well, remember, we found that there were 26 out of the 298 students that were studying both. So in this situation, that would represent the not A, because we're looking for the probability that they're not studying both languages. So the not of that, the opposite of that, would be the fact that they do study both languages, which would be those 26 out of 298. So I could take the 1 minus 26 out of 298, and that gives me 272 over 298, or as a percent, we would say it's about 91%. So it's about 91% of the students that do not study both languages. So there we have it. I know there's a lot of information here in this section, but hopefully now you have an understanding of the difference between situations that are mutually exclusive and those that are not, and how to find the probability of those. Again, that can be summarized as far as having a visual in this diagram. But you just want to remember that if it is overlapping, we have to subtract, for the probability, we have to subtract that overlapping amount. So with that, good luck now as you work on your assignment.